Hi there. Yeah, in last couple of lectures we learned basic fractals and then we looked at the plane transformations. And as I promised you in the last lecture, I will today discuss with I'll start with the iterated function systems, which can be used to produce fractals, simple fractals as well as complex fractals. But IFSs are very basic method to use to produce fractal objects. So let us rumble today and see how we can use this IFS systems. The iterated function systems, we call them iterated function systems as IFS is full form. And we see that the generating fractals by iterating a collection of transformations is the IFS method. So we generate fractals through iteration of several transformations. And as we noticed in the last lecture, that we were seeing these transformations were defined by 6 parameters, which were R, S, which were the scaling and reflection parameters, theta and phi, which were rotational parameters, and E and F, which were translational parameters. So given the six parameters, we can always find out, or we can always produce a IFS object which hopefully will be a fractal. So this method was mostly popularized by Barsley, which was basically based on some theoretical work already done by Hutchinson and Decking. So we give proper tribute to these people who worked for IFS systems. And now we use a simple example to see how this will work. We will use the example of Sierpinski's gasket. So we generate how a specific set of IFS rules generate a Sierpinski gasket. If you remember the right isosceles Sierpinski's gasket, you remember that it has triangles within the triangles and so on. And we also know that this gasket can be viewed as made up of 3 copies of itself. So each gasket itself is a copy of 3 copies, a copy of 3 smaller objects. And these objects are exactly half of their original size, both in x and y direction. So they were scaled by half and half, and basically there is no rotation in this, but a bit of translations are involved. So if you consider these 3 objects as this object, this object, so this object. So we need 3 set of transformations for this thing. And here are these 3 set of transformations are given. They are color coded. You see the purple color is the first transformation, red color is the second transformation, and the green color is the third transformation, and which will produce my original Sierpinski's gasket back. So and these are different values of R, S, theta, phi, E and F. Since there is no rotation involved, so you will note that all theta and phi values are 0. E and F for the first transformation, the purple one, they are 0, 0. So with respect to origin, there is no translation either in x direction or in y direction. For the green one, it has a translation in the vertical direction. So we have a f values as 0.5. For red, we have the e value as 0.5 because there is a translation of half of the original length from the origin of the basic size. And you see Rn and S values are half and half for all these 3 transformations, because each of these objects is half of their original size, both in x direction and in y direction. Now we will learn another property of fractal with this example, which we also discussed in the very first lecture, the scale invariance of the fractal object. So we will see the invariance of the gasket. So we will note that when we apply all 3 of these transformations together to the original gasket, we get the gasket back again. So by applying all these 3 transformations, not from one transformation, remember you have to apply all the 3 transformations in order to get the gasket back again. That will make, so simultaneous application of these 3 rules will give me a gasket back. So my gasket becomes invariant, it does not change. Variant means changes and invariant means no changes. So we say, in summary, we will say that the gasket is invariant under the simultaneous application of these 3 transformations. Okay, these are the three transformations, again color coded. Purple one is the first transformation, red is the second one, and the green one is the third row of the transformations. Now a question arises. Okay, you say this is a very simple thing. You started with the gasket and you get a gasket back. So what is new about it? And what is so peculiar or so spectacular about this? So a question arises, what will happen if I apply these transformations to some other shape rather than the gasket? Suppose I apply these transformations to the shape of your mobile phone or your table, or I take a picture of your table, I take a picture of you and apply these transformations to other things. What are we going to get? What will happen if I apply this transformation to the resulting shape again? That means you iterate over the system. You apply this transformation once and then you get some object, then you apply the same transformation again to the resulting object, and so on. So what will happen if we are iterating this process? Remember, we are saying this thing is a iterated function system. So these are the functions defined for a system, but we need to iterate it. So that's what we will see, and we will take a very general example. This is a general picture. So you have an object, a computer, a table, and so on. So this is this idea was applied to the sketch of this cat sitting with the computer and this thing. So we will observe there's a sequence of pictures that converges to the gasket independently of the starting shape. We'll see how. So we start with this shape. This is the original object. We apply these three transformations which we discussed in the last slide: the purple one, the red one, and the green one. So we apply all these transformations, and of course we are getting this particular object. All of you must agree that we will get this. Now what we do, we take this whole as an object and we apply this to the whole object. Now this is the purple rule, this is the red rule, which is the second one, and this is the green rule, which is the third rule. So we get this kind of picture now. Now we take this picture as the resultant picture and we apply all three transformations to this picture. See, we will get this kind of picture. Again, that picture is getting compressed and compressed, more and more compressed, but it is evolving into a fractal object. So you can now guess easily that this will indeed, over if we do 5 or 6 more iterations, it will look like a Sierpinski's gasket again. So we say that using the gasket rules, we saw that it will converge to the gasket. Whatever is the starting point, see, our starting point was not a gasket, it was an arbitrary shape, but applying the same rule, so it's the rule which are governing the gasket's shape, not the initial object. So because all the transformations are applied at each iteration in this, we call it as a deterministic algorithm, not a random algorithm. We are deterministically, we are determining something which is already defined and determined. So that is why we call it a deterministic algorithm. And this is how we can apply, we can show it mathematically also, or in a set theoretical in the set theoretical concepts. Suppose we call these transformations, this is the first rule, the purple rule, T1 xy. So what is the T1 transformation? Is x half, each x will become x by 2, each y will become y by 2. T2, the red rule is x becomes half, y becomes half, and there is a shift of half in the x direction, no shift in the y direction, so that is 0. T3 is the green rule, which is x half, y half, and there is only a shift in the vertical direction by half of the original amount. And this is my original object P0, which is a general object. And we are seeing here that each of these transformations, T1, T2, T3, etc., up to Tn, we can have n such transformations. They are all contractions. Contraction means the application of this transformation will contract, which it will reduce the size of the object. And P0 is any picture. So when we apply P1, what will be the P1? P1 will be T1 applied on P0, union T2 applied on P0, union T3 applied on P0. And this will give me this object. Then this object will become P1. I apply another set of iterations on P1, which will give me a new object called P2, which is this object. So P2 is T1 applied to P1, which is this, union T2 applied to P1, union T3 applied to P1. So if I have n such transformations, then I can do it for n such transformation. So the general rule is pk plus 1 is equal to t1 pk and t2 pk and t3 pk. So ultimately you will get this particular thing. Okay, so that gives me a Sierpinski's gasket in the thing. So this sequence will converge to a unique shape P. Why I'm saying this? Because P, when you apply, ultimately, as you saw in the Sierpinski's gasket, ultimately it will look like it is the only compact shape, the ultimate shape P, which will remain invariant under the simultaneous application of all the transformations. See, these things are still varying, but after a limit, you will not notice any variation. If it becomes this and we apply all such transformations, this will give me back the same picture. So this becomes invariant. So P is equal to T1P union T2P union T3P. So all transformation applied to P will give back P again. So that is, because of this convergence property, when the object converges to a particular thing, we call this P as the attractor of this IFS set of these transformation. So this is by definition we say this shape is the attractor of this IFS T1, T2, T3. So given on any general object, if you apply this set of rules to that object, it will give me a Sierpinski's gasket only, because Sierpinski's gasket is the attractor of this particular set of transformations. Okay. So this is how you apply these rules and get the fractal object. Now a question arises how to solve it inverse, how to invert this problem. Suppose in general, in nature, you will not have a set of rules with you. You will have something which is produced like a tree. You see the tree, now you want to find out what sort of transformations are applied to make the tree by the nature. So what happened there? So that is called an inverse problem. You want to invert the data, you want to invert the object to see, looking at the object, you want to see that what are the rules which govern this particular object. So finding the inverse problem means finding the transformations to produce a given fractal. That is called an inverse problem. So suppose you are given a fractal f, the inverse problem will be to find some affine transformations t1, t2, t3 up to tn, if there can be n number of transformations, for which f is invariant. This f should be same as t1f union t2f union t3f union t4f up to tnf. So here we present a simple method to solve this problem. In fact, this problem initially looks a very, very complicated problem. It looks like that it's almost impossible to find that. But when you look at it, at least for simple things, it will just take a couple of steps. Very, very easy. So there are solving this inverse problem, which it has only two steps to be taken. We use a self-similarity or self-affinity of f. And decompose f as f1u, f3u, f2u, f3u, and so on, where each fi, this fi, is a scaled copy of f. Remember, in the Sierpinski's gasket, we broke the Sierpinski's gasket in three different parts, where each of these parts looked exactly like the original part. So that's what we have to do with all such objects. We have to break this f so that it can be broken in n different parts, and when you combine these n different parts, they will look like the complete f, and each of these f different parts are some sort of a scaled or rotated copy of the original f. May not be the same scale, but it has to be a scaled copy. Maybe one of the maybe f1 is only half of the original size, f2 is maybe 1/3 of the size, and so on, and maybe f3 is rotated in a different direction. So that is the material, but only thing is each fi should be a scaled copy of the original f. Then in the second step, you will consider each individual fi, and you find an affine transformation ti, for which I can get TIF equals to Fi, for which if I apply the transformation to the original object F, I'll get Fi. So we find an affine transformation, which means we find these six values R and S, which are scaling parameters, theta and phi, which are rotational parameters, and E and F, which are translational parameters. So finding the value of these 6 parameters makes the inverse problem. So first step is the decomposition of the original object. Now, since the information, so we learned this, how to decompose things. In fact, it turns out to be very, very simple. It's not very difficult. Because the transformations can involve rotations, reflections, and scalings, you would know that, by different factors in different directions. As I told you, they may not be same for all the transformations. So decomposition is not always very simple, as it was for the Sierpinski's gasket. For other objects, it may be a little bit different. So we will show you some examples of complicated decompositions. Suppose this is the decomposition. Now, how do you decompose that? This particular fractal is a very instructive example for people who have already seen the gasket. So we intuitively we will just say, okay, this is a whole gasket, then less gasket, then less gasket, and so on. But no, see, the rule is the scaled object should look like as the whole object. So these are individual Sierpinski's gasket for a triangle, but they are not looking as the whole object. The whole object looks like a series of triangles reduced in size. So the primacy of this gasket in early example of fractals makes this shape is one of the easiest to recognize because it looks like a gasket. So we may say, oh, it's just half a gasket. See, if you just see in this direction, you will see, okay, it's a mirror image of that and it's just half a gasket. But no, that is not there. So we do not, because we do not have rules for making half of a fractal. We cannot make half of a fractal. We have to make the complete fractal. So the main thing which we learned here is that we are looking for the scaled copies of the whole shape, not to another imaginary shape. The shape which is present here, and the whole shape is not a gasket at all. So we have to see something else. The easiest way is we can trace the copies of the outline of the whole shape and then see that. But these days nobody traces things, so you just have to do it intuitively only. If you look at that, this is one of the possible solution. See if you break it in these 3 parts, this part looks like the whole object again. This part also looks like the whole object but shifted in x and y direction, probably, and this part is also looks like the whole object. Only thing is it is a reflected copy. It's a mirror image of the whole shape. So that is one of the this is one of the possible decomposition, and we can make 3 such rules to produce this fractal. Now again, this set of lines, if you remember Cantor set, so where the Cantor set was just a distribution along this line, you can see each filled part of the Cantor set is extended in y direction by unit length. So that is it's a sort of a Cantor set in 2 dimensions. So in the x direction, it's again the middle third Cantor set, and in the y direction it's just a line segment. So it's a multiplication of Cantor set and a line in the y direction. So again we want to look for scaled copies of the whole shape. So I can decompose it in this way. I can have it 1 by 3 of the original size, 1 by 3, 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 and then we can place them with some proper translational rules, and we can say, okay, this will produce this object back again. Now I can also break this in this different direction. So we will see that a little later. That was one of the way. Okay, additional problem is sometimes that these decompositions are not unique. That is the biggest problem. And in fact, in earth sciences, we see very commonly that our solutions are non-unique. Same thing here also. These decompositions are not unique. There are some examples here. So if you want to find a composition of this fractal into smaller copies of itself, we see this is one of the possibility. This is half of the original size and one of the decomposition, 1 by 4, 1 by 4, 1 by 4. And combining all these 4 things, this will give me this back again. But there can be other ways. Some people may define it in a different way. Maybe this way. This will here is a set of 1, 2, 3, 4, 5, 6, 7 set rules which will also give me the same object back after unifying all of them. So these 4 transformations or these 7 transformations both will give me this particular object. So there can be a non-uniqueness. That's what I want to emphasize here, a non-uniqueness of the decomposition. So that's why each fractal may have non-unique set of transformations which will produce the fractal back again. So we have already seen this example earlier. So same thing can apply there. We saw one of the possible way of decomposition was that. Another way of decomposition may be this. This also gives me, so instead of having 6 such values, I can have 4 such values and get the fractal back again. So that is, or that can also be there. Now the second step for each piece Fi, the first step is decomposition, and now for the second step, for each of these decompositions, we will find and affine transformations Ti, for which TIF is equal to Fi. So we want to find these transformations for all such decompositions which we did in the earlier step. So one way is again doing it manually, or tracing the main features of the fractal and cut out smaller copies of the tracing. And then to allow for reflection, we just reflect that, flip the small copies on the back trace over the lines on the front, then label the front image with a small f to distinguish it from reflection, and then indicate the original orientation. Now we place the small copies all together. Maybe some copies may we have to rotate and reflect, and then to produce the original fractal again. But we can do it on a computer also. So here are a few examples for such things. Now this fractal can be decomposed into 3 pieces. Just note that the top and bottom left pieces have the same orientation as the entire fractal. This top one and the bottom one, it has the same orientation, but this the right one is the reflected across a vertical line, and each of these pieces is half of the original size. So that is how we give this number. Here we see the purple one, the 0.5, 0.5, or then no rotation, no translation. The red one has minus 0.5, that means reflection across the y-axis. That will give me a reflection, minus 0.5. So minus 1 is multiplied to 0.5, and then after doing that, we shift that by 1, not by half, by 1. We will see how. And the green one is again scaled by half and shifted in vertical direction by half of the original size. So these are the there's minus 0.5. And another one here, you see here, this one again into 3 pieces and similar rules. Again, the top and bottom left pieces have the same orientation, while the bottom right piece is rotated. It's not reflected, but it's rotated. So and keeping in mind that our transformation rules allow only rotations fixing the origin, so we have to see after the rotation where this object will lie, and then we have to see how much translation is required. So when we rotate this by 90 degree in x direction, 90 degree in y direction, it will go towards at this point, and then you need to shift it by 1 unit to make it to bring it here. That's why a translation of 1 is required here. So that's how you will see, and then you will have this as your assignment, that you will have to find IFS rules to generate each of these fractals. As you see those fractals, you can see those, and you will have to find the IFS rules to generate these fractals. This fractal, first of all you have to decompose them and then find this, and then this is just a practice test for a sort of an assignment to you guys, which you can practice and see how do they work out. So I think I'll stop here today, and we will discuss more things in the next particular presentation. So we stop now, and thank you very much for listening. Thanks.